You walk into the grocery store, head to the snack aisle, and your favorite potato chips have suddenly disappeared. The reason for the empty shelf is a geopolitical crisis thousands of miles away in the Strait of Hormuz. But what does heavy oil have to do with your potato chips? We usually picture modern factories as giant electronic machines. As long as the power grid is humming, we assume the robots, sensors, and conveyor belts keep moving. But high-volume manufacturing requires massive amounts of physical heat. You can't fry millions of potatoes with just a motherboard. You need sustained, intense temperature. The global supply chain relies on a hidden bloodstream of heavy fossil fuels to provide that raw thermal power. If that fuel stops flowing, the entire assembly line dies, even if the lights are still on. Combusting heavy fuel is historically much cheaper and more efficient for generating high-temperature industrial heat than using electrical resistance. Think of a modern factory as a hybrid organism. Electricity acts as the nervous system, powering the computers and motors, while steam and heat act as the actual muscle doing the heavy lifting. Deep inside the facility, heavy oil is burned inside a massive centralized boiler to create high-pressure steam. That steam is then piped across the entire building. It performs multiple jobs simultaneously, from heating vats of frying oil to drying packaging, sterilizing equipment, and cleaning the floors. Because the entire factory relies on this interconnected web of thermal energy, a sudden disruption in the external fuel supply will instantly paralyze the facility. If fuel is this critical to survival and incredibly expensive to buy, why are so many industrial boiler and steam systems dangerously outdated and constantly leaking heat? The energy efficiency gap shows how profitable energy upgrades are ignored, creating a massive gap between potential ROI and actual invested capital. The main cause? Capital allocation. Executives pour funds into new production lines, leaving the bucket for background utility upgrades completely empty. The second cause is departmental friction. The facilities team wants to upgrade boilers to reduce costs, but the production team refuses to shut down the manufacturing line for the installation because halting it immediately hurts their specific output metrics. Finally, the data is invisible. Energy loss happens slowly across thousands of dispersed pipes and vents, making it nearly impossible for executives to see exactly where the financial bleeding is happening. Large corporations hemorrhage cash and carbon not because they lack the engineering technology, but because their internal organizational structures are blind to the value of thermodynamic efficiency. Right now, the industry is being squeezed by an impossible triangle: unpredictable geopolitical fuel shocks, soaring energy prices, and intense regulatory pressure to decarbonize. To survive, cutting-edge manufacturers are turning to digital transformation, or DX. It integrates digital technology into all areas of a business, breaking down organizational silos and finally making thermal energy consumption visible to executives. Factories are deploying IoT sensors and digital twins, which are exact virtual replicas of the physical plant, to constantly monitor the hardware. These systems instantly detect invisible steam leaks and inefficiencies before they can drain profits. They are also introducing demand response. This is a strategy where advanced factories act like massive batteries, dynamically dialing down non-essential equipment during peak hours to stabilize the external power grid in exchange for profit. Industrial survival now requires shifting energy from being a passive monthly utility bill to an actively managed, digitized operational asset. This thermodynamic bottleneck dictates the future of the digital economy as well. The explosive growth of artificial intelligence has transformed the server racks in modern data centers into massive thermal crisis zones where computation is entirely limited by heat generation. The tech industry is desperately transitioning from traditional air cooling to advanced liquid cooling, pumping fluids directly to the chips just to prevent high-density AI servers from literally melting. Whether you are processing neural networks or frying a potato chip, mastering the physical flow of heat and energy is the invisible, ultimate constraint on human progress.